AgriEnergy Solutions, the solutions part of our business now has been in place for 4 years, I believe. So that's relatively new, but AgriEnergy dates back 30 some years. So, until by our great work there. So we're 7 staff. In the staff, raise your hand. Probably everybody almost knows everybody, but if you have any questions today or issues or problems, grab one of us. We're approximately 65 dealers and consultants, and we've got dozens of top-notch partners and vendors that we work with. So normally, if you need something, if we don't have it, normally we can help you find it. So what do? We consult, we interpret soil tests, we interpret tissue and sap tests, we assist in prioritizing your budget, we manufacture, source, supply, deliver fertilizers and biologicals. We visit your farms to evaluate the progress that you're making, and we strive to maintain and improve your most important asset, your soil state of health. How healthy is your soil? Is it working for you? Do we need to improve it? Is it doing its job to the best of your ability, to the best of its ability? So things to look at. How is your decomposition? Do you have 2 or 3 years of crop residue laying out there that you can identify? We really like for that crop residue to be gone by midsummer. So is your residue decomposing rapidly? When does your soil warm up? If your soil is alive, it'll stay warmer a little longer into the fall, warm up a little quicker in the spring. How good is your tilth at planting? How's your seed bed? If you're no-till, that planter needs to do its job. You need good tilth so you get the seed placed right. If you're tilling, how many passes do you have to make to get that seed bed in shape? If your soil is alive, it tends to come into shape much quicker. How healthy is your crop? Do you have any obvious nutrient deficiencies? Do you have any hidden hungers that need addressed? How did your roots develop? Your roots are a reflection of your soil. I thought that was an interesting comment right across. Especially in corn, if you dig up that corn plant midsummer, you can pretty well tell what the structure of the soil is. Do you have compacted layers? It does give a picture of what your soil is. How good is your tilth at pollination? Something we don't talk a lot about, but you'll hear several lines of thinking like that today. That crop needs to finish strong. We need good tilth at pollination. Have you maintained your yield potential? As they say, the greatest yield potential we have is when we take the seed out of the bag. How many things do we do to mess it up? How good is your tilth at black layer? How is your water use efficiency? As your soil comes alive, you need to add less water if you're in the irrigation areas, and your crops stay cooler with the water. How and why? How do we create season-long tilth, and why is it so important? So we're saying we need good tilth at pollination, we need good tilth at black layer. We need to finish that crop strong. Is your soil prone to compaction? Is your soil spongy underfoot? Does it pond easily? Does your infiltration and capillary action need improved? We get that big rain, we want it to soak in. Then through capillary action, we need that soil in the subsoil moisture to wick back up to take care of our crop. So does that need improved? Is it working well? Again, the water use efficiency, it comes back to the pore sizes. When we have good tilth, it seems contradictory to say that we can get water to soak in better, but yet our soil drains quicker so that we can get out on the field. But it's due to the pore sizes. So if you have good tilth and you have that coffee ground structure, we've got large pores and we've got small pores. Large pores help the water infiltrate when we get that rain. The small pores is where we can hold water to feed the crop longer and to keep the crop cooling. Why is this tilth so important? University of Illinois research that we fell into and ran across recently. They're using naturally occurring isotopes of nitrogen and found 67% of the nitrogen in the corn came from the soil, not from the fertilizer. That's an amazing number. 67% of the nitrogen came from the soil, not from the added fertilizer. Fall applied ammonia, 21% of the nitrogen applied made it into the grain. Using a nitrification inhibitor did not improve the nitrogen uptake. So that paints a picture, I think, for all of us to think about, and as to why that soil tilth, that soil health is so important. And when we see some really special things happen in fields, you can kind of relate back to this. When you see that soil really tilthy late in the season, it's soft underfoot, it makes the difference. Split applications of nitrogen, sidedress, and Y-drop help some, maybe around 10%, but still most of the nitrogen came from the soil, not the fertilizer. So even spoon feeding it, most of the nitrogen still came from the soil. So this is one of the researchers, Dr. Mulvaney. If the soil is the main source of nitrogen for crop uptake, which it almost always will be, we need to take the soil into account. It's just that simple. Otherwise, with factors like timing, rate, placement, form, we're tweaking, but probably won't find a miraculous increase in efficiency using these approaches. We really should go towards adjusting rate according to soil supply and power. Half of the yield is made the last 30 days before blackberry. So again, finishing that crop out strong, that tilth at pollination time, at maturity is such a very, very big deal. Late in the season, nitrogen and potassium come into play in a really big way. So potassium, availability of potassium can increase with various amendments. Manure will increase potassium release and decrease potassium fixation. And they're not talking about the potassium applied in the manure. They're talking about conditioning the soil amendment, getting the soil in shape, getting the tilth there so that these things happen. Phosphorus applications increased root mass, photosynthesis, and leaf water content when stressed. This increased potassium availability during all stages of corn growth. Several amendments they found helped potassium uptake early, but it didn't carry through to maturity. So manures help potassium availability, and especially think about late in the season. Phosphorus helps. And why does the phosphorus help? Because you're increasing the root mass and photosynthesis. You've been around our meetings, we like to talk about root exudation. If you have more photosynthesis, you're going to have more carbons put out the root, stimulate more biology, increase your tilth. It kind of paints a picture. This is Eastern Ohio. We're in farmer that's new to us, did a plot control to the left, 1 gallon of SP1, that was the old version of MVP, and then 3 gallons to the right. Of these soils, silty clay loams, they really have trouble getting potassium available. But notice the color difference in the soils. The one to the right, particularly dark, a lot more soil activity, a lot of biological activity, more humus formation, more microbes living in that soil to the point that the soil darkened and held more water and make considerable difference in the crop. So soil tilth, how do we do it? What do we talk about? We're talking about inoculating with biologicals. Residue degradation is very important. Something that we want to see to start late summer, early fall, is to get that residue degraded. You stimulate nitrogen fixers, which means we're pulling nitrogen out of the air. You stimulate those organisms with a very high carbon to nitrogen ratio, you can start that tilth in motion. We see that happen routinely. And why is that? For these nitrogen fixers to do their thing, they have to work anaerobically. So they put out polysaccharides, which help the soil to cling together, stick together, pull particles together. So you get that soil aggregate that we like to talk about, that actually in the core of that aggregate, it's anaerobic to fix the nitrogen. So there's an opportunity if you have corn stalks or wheat straw out there with the high carbon to nitrogen ratio to stimulate these organisms and bring it down the path. That will improve the tilth. You'll put more nitrogen in your soil. The soil will darken. It's how we like to see you start if your soil is lacking in the ability to degrade that residue. Utilize the root exudates. There's literally tons of carbonaceous materials that are put out the roots into the soil. So we like to use seed treats and starter applications with inoculants so that we can inoculate those roots, and then as the roots grow out through the soil, the microbes will go right with them, and you can change the soil. One of the best ways to change your soil, to make your soil more tilthy, is to grow a good healthy crop with this happening. You'll loosen the soil up. Sidedress, always another opportunity. If you're putting fertilizer out there, put some kind of inoculant with it as well. And then foliar applications, like to stabilize, buffer, inoculate those fertilizers with biologicals. There's a lot of things happening on the leaf surface that are not even totally understood, but there's an opportunity there. If you're foliar feeding, have some biology going with it too. Not a lot, but small amount. So leave me with this slide. I ran across this and I thought it was pretty cool. 7 fascinating facts about soil. Soil is complicated. All the ratios we talk about, the soil structure, the texture, there's a lot to it. You can spend your life learning about the soil. So the soil is complicated. The soil is alive. The soil can die. The soil should be treated as a non-renewable resource. We can make soil, but it's a really slow process. Mistreated soil releases carbon. Well-managed soil sequesters carbon. Soil is not dirt, and we have the power to protect and improve the soil. So you'll hear a whole lot more about all these things throughout the day. And with that, I think we've got Ken.
Good morning. Kind of looks like church. All the empty seats are up front.
See the screen come up here.
Yeah, there's plenty of room up front. And the slides will look better up if you're up closer. So I want to talk about some of the basics of regenerative farming or biological farming. And, you know, that's something that we've been doing for several years. And I do believe in regeneration. I believe that God can regenerate the souls of men dead in their sin through faith in Jesus Christ into new life. And I also believe that we can regenerate soils if we follow God's principles. Now, I don't want to sound like God wrote things down on a tablet and handed it to AgriEnergy, but these are precepts that we've talked about from the beginning. Dave Larson talked about these same 3 things when he founded AgriEnergy in 1988. And in my 40 years of renewable farming journey, I think they still hold true that these are the 3 pillars. Number 1, manage air and water in the soil. We need to create an environment for roots to grow and for beneficial organisms to thrive. So we need a soil that is porous, that can get water in the soil, infiltrate rain, but also air, have good gas exchange in the soil. And that's a foundation. I get in a lot of fields in the summertime, and I think oxygen is probably the most limiting thing in the soil, more than any other nutrient. And when your oxygen is short, a whole lot of other things are apt to be short too. Secondly, we want to manage crop residues so they decompose rapidly. We want to feed microbes that break down those residues so they can do their work and recycle nutrients, sequester carbon, and build organic matter. And third is manage crop fertility. And if we do a good job on the first 2, this becomes a whole lot easier. But plants need nutrition to grow and to produce the crop, but they also need nutrition to produce root exudates that feed the microbes. And that's how we really build soil, is building that microbial population underground. So tilth does matter, especially if you're trying to farm biologically. If we have good soil tilth, again, we get better water infiltration from the rain. And not only that, when the soils dry out in the summertime, if we have good tilth, water can move up by capillary action back up into the root zone. What happens when we have a hard pan is that water quits moving up when it hits a change in density or soil particle size. But if we have good tilth, that barrier isn't there. So we can get water to go down, come back up, and we can get air to do the same thing. It matters for the function of soil microbes, largely because we have oxygen in the soil. Most of your beneficial organisms require oxygen, and most of your pathogens favor anaerobic conditions or lacking oxygen in the soil. So if our microbes are functioning, we get better nutrient use efficiency. It takes less inputs to grow a crop. Ease of tillage is obvious. If your soil's tilthy, any tillage you do, it's going to take less horsepower to do it. And you'll probably need less tillage if your soils are tilthy. It also impacts weed control. And if you're organic, this is a huge deal. Why is that? If the soil can breathe, it's able to exchange gases and get rid of CO2 and methane and other things that trigger weeds to germinate. So soil tilth has a big impact. So the bottom line is, if you don't have soil tilth, you are forced into a chemically dependent system. If you have tilth, that allows you access to the biological system. Factors of tilth. So we want to manage air and water in the soil. Again, it's all about the pore space. So there's two aspects to that. One is flocculation, a clumping together of soil particles into larger aggregates. And the other is aggregation. That's a biological process where microbes secrete polysaccharides that glue individual soil particles into larger clumps or water-stable soil aggregates. And that's what gives you that coffee ground soil tilth that we want. So I mentioned the chemical process. That's largely dependent on soluble calcium. We're looking at a chart here, the relative flocculating power of different cations. So for flocculators, there's sodium and potassium. They're a 1. Magnesium's better at 27. Calcium is a 43. That's why we talk a lot about calcium to magnesium ratios. If we have enough calcium there, the soil can flocculate and create that pore space, give the microbes a home to work so they can build water-stable soil aggregates by gluing soil particles together. So how do we get soluble calcium? There's two common dry amendments. One is high calcium lime, and the other is gypsum. You're going to hear about another product later on this morning to do that too. But they're both calcium products. Lime is calcium carbonate, and we need that if we need to adjust our pH if our soils are acidic. Once we get pHs above 7, calcium carbonate is not very soluble in the soil. Gypsum, on the other hand, is soluble at all pHs. However, it will not raise your pH. So if you're acidic and you need to raise the pH, gypsum will provide calcium, but it won't change the pH. And pH is important. It affects the availability of a lot of other nutrients. Some things get tied up at a low pH, other things get tied up at a high pH. So on the liquid side, we've used calcium nitrate-based products for years to provide soluble calcium. Currently, we have our AgriCal, which is calcium nitrate-based with micronutrients and some sugars in it. We have our PrimCal, which is the calcium nitrate with humic acid. And then for organic growers, we have the MicroCal O. And those are liquids that will increase the soluble calcium in the soil for a short time in the growing season. And they will help change soil tilth. So there's a lot of things that impact soil tilth and structure. A lot of variables, of course, soil type is a big one. Some soil types just don't lend themselves to being tilthy naturally. Tillage practices, certainly if we over-till our soil, it's going to be hard on till. But in a lot of cases, we do need some tillage to get air in the soil so the microbes can work. But we have to realize tillage is a temporary Band-Aid. Long term, we need calcium and we need biology. But tillage can jumpstart that process and get things turned around quicker if it's wise tillage. Crop rotation, generally the more diverse cropping rotation we have, the better tilth we have, the better microbial diversity that we have. Fertility, we'll talk about the connection of that besides the obvious calcium to magnesium ratios, but plant fertility does matter too. And then again, microbial activity and diversity. We want a broad spectrum of microbes out there, bacteria, fungi, other things. So we want that diversity. We really believe in adding biology in the soil because we feel like there's times that we need to speed up what's naturally happening in the soil. And also it gives us a chance to supply organisms that might be missing. So why would we add biology? Well, microbes can enhance nutrient cycling, enhance nutrient extraction and uptake. Some microbes can fix nitrogen, pull it from the air and make it available to the plant so you don't have to purchase as much. A lot of organisms are good at solubilizing phosphorus, potassium, calcium, and other things. Stimulate root growth and root exudation. Increase plant health and tolerance to stress. And then also increase soil health, porosity, and tilth. And again, when that happens, we increase water infiltration and also water holding capacity as we get more carbon in the soil. So this is a slide put together by Dr. Robert Primmel from the University of Missouri, just showing different functional groups of microbe activities. And you can see there's a lot of things there, and one microbe doesn't do all that. We need different microbes for different purposes, and that's why we need that diversity. So we want all these microbes functioning in our soil to do these various things. So how do we build our microbial population and diversity? We want to adapt cultural practices that promote microbial growth and multiplication. And we want to feed existing microbes, the ones that are already in our soil. And that can be done with sugar, with carbon, with nutrients, cover crops. You hear a lot in regenerative farming circles about always keep a living root in the soil. What's the main reason for that? A living root is going to put root exudates in the soil that feed the microbes. And if we have a living root growing year-round, then we're feeding microbes year-round, not just a few months out of the year. So we can do the same thing in our cash crops. If we have good, healthy cash crops, they're going to put out root exudates that feed microbes too. And then good residue management. We want to capture the carbon that's in that residue, but also cycle the nutrients in it. And another way to build biology is to inoculate with additional microbes. Do it at times a year where microbial nutrients might be lacking, or maybe we're improving the diversity of the microbes in our soils. So the best way to build soil is to grow healthy plants, and fertility does matter for that. Well-fed crops allows well-fed microbes. So again, we want to manage our crop residues encourage decomposition, feed the microbes, and cycle the nutrients. Does residue management really matter? Do carbon to nitrogen ratios in the soil really matter? Here's what we think good residue management is. Number one is till plant residue into the aerobic zone. When I came to AgriEnergy in 1991, I had a history of being a ridge tiller for 10 years, where we grew corn and soybeans and rotated. And our system was we throw up a big ridge with the cultivator this tall in 30-inch rows. And no other tillage was done till we planted the next year. We didn't do anything to the residue. We come in with the planter, scrape off the top of that ridge, plant a nice clean seed bed, great soil tilth there, throw all the residue out in the middle. But we hadn't touched the residue. And, you know, Dave would talk about we need to till our plant residue into the aerobic zone. Yeah, but that doesn't fit our system. We're ridge tillers. And yeah, that just doesn't work for us. And the light bulb came on for me when I heard Alan Savory speak one time on holistic grazing. And he was comparing grazing on government lands versus right across the fence, well-managed intensive grazing. And of course, on the government land, they just don't want much animal impact. They don't want to disturb the environment. In intensive grazing, they're running large number of animals there for short periods of time. So they're consuming some of the forage, but they're trampling a lot of it in the ground with their hooves. And the pictures right across the fence from each other were like night and day. Under intensive grazing, there was lush forages. It was nice and green, all kinds of vegetation there. On the government side, it looked like a desert wasteland. Why is that? When those cattle trample that residue into the soil, it captures that carbon. If we're not putting our plant residues in contact with the soil, in the course of a year, a lot of that carbon can just volatilize up into the air. We don't capture it. So it's hard to build organic matter. And it's understanding that scenario that this whole residue management thing began to click with me. So, you know, again, if you're no-tilling, we're not telling everyone they have to till, but you need to get your residue in contact with the soil. The microbes that decompose the residue don't climb up the corn stalk for the most part. They live in the soil. So if we want it to decompose, it needs to be in contact with the soil. We want to narrow the carbon to nitrogen ratio like in the compost pile. Organic matter is about a 10 to 1. A lot of our crop residues start out at 100 to 1. So we need some nitrogen to get it back to create organic matter. You know, that can come from livestock manure, green manure crops. But we do want to avoid excessive nitrogen. So what does nature do if we put too much nitrogen out there? It wants to get back to that 10 to 1, so it actually burns off carbon. So it's hard to build organic matter if you're using excessive amounts of nitrogen. And then we want to inoculate with biology. Again, we're trying to speed that process up, get the residue to break down quicker than what would naturally happen. So that's a big part in nutrient cycling, getting that crop residue to decompose. Crop residues represent a tremendous energy and nutrient reservoir. So the energy trapped in organic matter fuels the metabolism of soil microbes. So then we get mineralization or release of nutrients in the soil. Immobilization is the process of nutrients being tied up in the cells of microbes. So once we break those nutrients free, the microbes can contain them in their body and give them later for the crop, kind of a time release fertilizer. This is a picture from Ben Frieden's warehouse plot. Ben is with us today here. So Ben, I want you to correct me if I get something wrong here. But this is the lawn around his warehouse. His warehouse is over here. I think it was 2 years ago, he tilled up a strip here and planted alfalfa. Here is a little patch in the corner of alfalfa that he left, but the rest of that he tilled up and planted a 16-way cover crop mix. This picture was taken on August 22nd this past year. And just prior to seeing that, he tore up sod here. And you can still see some remnants of the sod here, but we've got this 16-way cover crop going on both sides here, after alfalfa and after freshly tilled sod. Look at the difference in the color of the soil. We're much darker here. Then here is a month later, September 24th, Ben sent me pictures. And doesn't show up real good, but on this half right here, you can see the cover crop short. It's kind of pale green. Where it was growing here, it's dark green. And here we're looking at same angle as this picture. You can see the height difference. Why is there such a difference? Yeah, part of it's probably because it's following alfalfa. But what else has taken place? Here's soil tests from the same two areas. We're talking 5 feet apart here. Organic matter went from 3.1 to 3.6. There's a reason that soil is darker. Phosphorus numbers jumped, potassium numbers jumped. So by tilling that sod down 2 years ago, it had time to digest, capture the carbon, cycle those nutrients. They're showing up in the soil test. They're showing up in the crop growth. So again, it has to do with managing residues and getting the right carbon and nitrogen ratios. So again, residue management. If we're planting into an environment that has a carbon to nitrogen ratio of 30 to 1 or higher, we have nutrient immobilization or tie-up. So, if you're planting soybeans in cereal rye that's really big, that may not be a big deal. Soybeans don't need a lot of nitrogen early on. They can do okay with that. But if you're planting corn in that environment, you're asking for trouble. You're swimming uphill. If we can get our carbon to nitrogen ratios to 15 to 1 or less, we get nutrient release. And those nutrients are ready to take off and feed the crop. And a lot of cover crops, 8 to 9 inches is kind of the breaking point. Once they get over 8 to 9 inches, we get a lot more mature carbons that are harder to break down. And when we plant into that cover crop and the carbon in it is actually going to steal energy and nutrients out of the system for a while. So if we're in that scenario, we need to front load nitrogen if we can. If you're organic, that's harder to do. But if we can avoid that situation, we're going to get along better. Here's a couple illustrations. This is a field of organic corn in northeast Indiana. Ended up making 266 bushels per acre. And I said, well, what did you do to manage it to get a crop that looked like this? Well, it was in pasture the year before. He plowed it up in August, so he turned that sod under, put the residue sod to start the decomposition process, seeded a cover crop mix, one that either died out or didn't get a lot of growth in the spring. So most of that digestion process took place prior to growing the corn crop. This is some organic corn in west central Indiana. That his corn made 290 bushels per acre. You see just how dense that canopy is in there. Same scenario, terminated a pasture the summer before, seeded a cover crop, but you know, it was pretty well through that digestion process. The interesting thing is I was on that farm 25 years ago, and that was the poorest rundown soil you would ever want to find. And now he's growing 290 bushel organic corn. And that's not uncommon for him. His goal's 300 every year. This just shows research done by Douglas Plant Health on DPH Bio on the residues product, putting it on corn stalks ahead of beans. And it showed that where they treated the residue, potassium numbers went up 23 pounds, phosphorus numbers went up 31 pounds on a soil test. And you can see the difference in canopy. And here it is up close. You see more growth. Look at the size of the leaf. Why is that? We've got more nutrients soluble and available to the plant. So investing in biology, is it a needless expense or a necessary investment? I'm going to propose that maybe it should be the backbone of a fertility program. So here's what we would consider good residue management, or the products that we use. The digester or Residue WS, the microbial package that goes on at 1/10 of a pound per acre. Then we like to put a food source with it to jumpstart the microbial population so they can start working on the residue. Typically, they're going on at 1 to 3 gallons per acre. And here are some of the choices. Again, the Prim-Cal is a humic acid, calcium nitrate base. Boost is a molasses product. Premium 21 is just a humic acid with amino acids in it. For organic, we've got our Micro-Cal-O, which has fish hydrolysate in it. Dramo, the high phosphorus fish, that's an excellent food source. The TerraFed, another molasses product, or we can use combinations of these also. What are the benefits of good residue management? Improved soil tilth. If we have improved soil tilth, we have a better seed bed to plant into. We get more uniform emergence, better early growth. We talked about early or less weed pressure due to gas exchange in the soil. Breakdown of phytotoxic compounds. You know, that might be pesticides from the previous year, but it can also be some of the byproducts of early stages of decomposition that are phytotoxic or alleliopathic to the next growing crop. We have less tie-up of nutrients. There are more clean available form. So that allows us to get off to a faster start on our next crop and reach our maximum yield potential. So we're going to switch gears here from residue management. What can we do in a growing crop? And we want to focus on the rhizosphere. The rhizosphere is that soil immediately surrounding the plant roots. That's where the majority of the microbial activity happens. That's where we can really impact the situation in the soil. And that is influenced by the root secretions, rhizodeposition, soil, and the soil microbes, bacteria, and fungi feed off of that, sugars and lots of different compounds that plant roots put out. So MVP is a liquid biological product that we use, and we're putting out a diverse package of microbes there and also things that stimulate root growth. So it's a small thing that can make a big change if we get this MVP with the microbes working in that root rhizosphere. So it stimulates the plant to grow more roots. The plant roots produce more root exudates. The exudates feed the microbes. The MVP supplies the microbes and makes sure we have a diverse package there. So we can actually use that plant as a microbe incubator to keep building our microbe populations through the season, as long as that plant is putting out root exudates. So some of the uses, we can do a pre-plant broadcast, rates maybe 1 to 3 gallons per acre. In furrow is a great place to impact that rhizosphere, and we can do it right from the start of the season. Impact those plants from the beginning days. Again, 1 to 3 gallons per acre. We can add it at cypress, 1 to 2 gallons per acre, foliar, 1 to 2. Most growers aren't going to go at the top end of every application, but a lot of our conventional growers will use 2 to 3 gallons for the season and split it up among whatever of these applications fit their operation. A lot of times organic growers are using higher rates, maybe 3 to 5 gallons or even higher in the growing season. And one of the reasons we're after the nitrogen fixation that we get from the MVP. So here's some cost-cutting ideas for 2025. Do our best to capture nutrients from crop residues. The biggest bang for the buck is biology on the seed or in the row. Inoculate roots early in the season. Get the microbes working for us. Cut back on starter fertilizers if our P levels are good, phosphorus, or if we're planting in more soils. And stay on the low end of nitrogen inputs, and to do that, we probably need to be split applying. If we're on the weekend and we get into wet weather, really wet weather in May and June, realize that you may have to adjust your plan and put on more nitrogen than you originally wanted to because of loss from leaching. Do our best to maintain soil tilth so the microbes are functioning and we don't have to purchase all our inputs. Keep the microbes fed. And then utilize plant testing in season to ward off problems. The soil, so chopping corn heads, maybe a vertical till machine the size the reds do, but the main thing is just get it in contact with the soil. Tools like an airway or a smart till, a rolling kind of aerator. Yeah, we can still do very minimal disturbance, go in with a no-till planter in the spring after those tools. But yeah, we've got a residue in contact with the soil and we've sped up that decomposition process. Any other questions? Okay, thank you.